Okay, well, thank you for the invitation. It's actually a pleasure to be here. I think last time I talked in this room was probably about 6 years ago. Anyway, so this is in fact, a project which started with Valeri about that time, about 6 years ago, and then it's been developing a little bit with him, so I'll remind him as well what the entire story is about. And then I kept on doing things related to this with Jan Veziu and Sundar Sudaraman. So Jan is a postdoc at the University of Arizona, and Sundar is my colleague there, and they're probabilists. So together we worked on more technical probability-related aspects. So I'll get to talk about that in the very end. Okay, so I'm going to start with this drawing, picture which I stole from one of papers of Oleg Larentovich. So his group was doing experiments on chromonic liquid crystals, and that's the primary motivation for this entire study. So as you most definitely know, so chromonic liquid crystals. Yeah, sure. So the chromonic liquid crystals are a specific type of molecules which kind of flat, and they look pretty much like disks. And one of the specific features is that they don't really like to be exposed to the solvent, to water in this case, with the flat parts. So they create these stack-like structures. So Oleg's group, they have been doing all kinds of experiments, in particular some experiments related to elasticity and measuring elastic constants for these kind of pneumatic, sort of self-assembled rod suspensions. And they found that, generic type theories don't quite explain the experimental observations well enough. And so there's an interest in terms of understanding developing some sort of Onsager style models for these chromonic type liquid crystals, where you would have distributions perhaps not just of orientations, but also over the sizes of these structures. And so that was the motivation. And so here is the schematic picture. Sort of I'll try to repeat the same things several times. So if there's anything unclear, please ask questions. I'll be happy to explain it, especially in such a small audience. We can pretty much discuss anything you like. The idea is quite simple. So abstractly speaking, you have a bunch of monomers, which we'll call monomers, and then M in this case, and then you create a bunch of polymers out of them. Polymers, so aggregates, are some kind of structures which incorporate these monomers together. Yeah. And so let's start learning the notation, which will be showing up every other slide. So pK will denote the number of polymers which contain K monomers. So that's the number of polymers of size K, right? And the question is, even if we forget about the entire complexity here, where you have orientations, that was actually the first thing we tried to do with Valeri at some point. We tried to, okay, let's jump into kind of hot water and see if we can do it. And then it turns out things are not as simple, so let's forget about orientations. In fact, for the entire talk, we will not talk about that, but just think of the size distribution of these aggregates. So as the number of monomers tends to infinity, can we tell something about the behavior of these pKs? So how does the number of polymers containing K monomers behave as number of monomers tends to infinity? So essentially that's the question that we'll be answering, and there'll be some mathematical model for that, and we'll see what happens.
Why do you call them polymers? It's just aggregates, clusters.
You're right. There is no particular reason to, but I had to call them something, and
I don't know.
It's probably would be better to call them aggregates of some sort, clusters. Yeah, but
I mean, if you don't have any orientation and they just aggregate in the spherical sort of fashion.
Yeah, you're absolutely correct.
I think we would call them clusters.
Yeah, that is true. It's just in the beginning when we were thinking about it, we were mostly looking at linear
Okay.
structures,
Yeah, but these things are not
which
linear.
you can think of.
If you throw away the orientations, you're not going to get
Yeah,
anything linear.
that is correct. So, yeah, in fact, very soon I'm going to show you a few, another picture where like the polymers are not necessarily polymers at all. So you can think of them as energy levels or something. Yeah. So I'll make this first distinction, and again, this is purely by analogy with physics, but there is no true physical motivation for this kind of classification. So I like to distinguish like what I call quantum ensembles and classical ensembles, and you can think of it like that. So if you have 4 monomers and you create 2 polymers out of them, so one has 3 monomers, and then there is another one which just has 1, like this. Like if you think that all monomers which form these structures are indistinguishable, like thinking of quantum particles which are indistinguishable, then there is only one way to do it. So there is one monomer, one polymer containing 1 monomer, and then another polymer containing 3 monomers. However, if you start distinguishing the monomers, then actually there's way more possibilities, right? Because you, out of these 4, there's 4 versions of this picture where you saying, okay, which of the 4 is that separate one, and which the remaining 3 form the other polymer. So this configuration would be distinguishable, and that's what I wrote here. So you can think of quantum monomers as partitions of integers, whereas classical monomers, they will be related to partition of sets. Like in this case, this is a partition corresponding to 4 equal 1 plus 3. So I took a number 4 and I represented it as 1 plus 3. There is all the ones are identical. However, this is 2 different partitions of a set containing 4 elements, and if you have these different colors, it's say 1, 2, 3, 4. This would be 4, 2, 3, 1. Yeah. So this partition of sets, they're slightly different, and so there would be these combinatorial factors. So if you think of, remember, pKs are number of polymers of size k. So for example, here P1 is equal to 1, P3 is equal to 1, and all other pKs are equal to 0. There is no polymers of the size. So, and there is only one configuration. Now in this case, there will be this many configurations corresponding to a set of pKs, because if you think this is pretty much just a multinomial distribution, so we take m factorial, total number of monomers, and then we're pulling pK polymers of size k, within which they indistinguish. We don't actually have internal structure for this particular talk, and then polymers of size k, they themselves are indistinguishable. So that's why there is this pK factorial.
To clarify, you call them quantum or classical, but if the particle were of the same color but classical, you would still fall in the first case?
Yeah, so that's what I'm saying. So what I'm well, yes and no. You see, no, not truly. Okay, it's actually a very delicate question. So in fact, I also talked about this a lot to Dmitry Golovati. You probably know him. So when physicists do experiments, you kind of derive certain, you measure certain averages, and you understand, okay, so here is distribution of this and distribution of that. We have some average measurement. But once you're trying to establish true statistical model, it's not quite obvious which one it is. So in the end, you will see that either this or that can actually lead sometimes to the same result. But it's not quite clear. So now, if you're thinking of, say, taking red balls and putting them into an urn, you will still have classical ensemble. It will not be quantum. So quantum is truly indistinguishable in a way. It's not so painting 3 different balls in red color will not make them quantum particles in that sense.
No, but I see a major, a different problem, more quantum and classical, with the distinguishability. For example, if you try to apply this to, say, colloidal particle or nanoparticle, they will be very similar, but not exactly with the same number of atoms. So in a sense, they are distinguishable.
Yes.
But for any practical purpose, and probably for the statistic of getting meaningful results, they might be.
I know, I know exactly what you mean, and I do not have a good answer to that, because in fact this is something that once I establish some ensembles, which sort of you build on top of, so you think of these things as a uniform sort of measure on partitions of sets or integers, then you add certain Gibbs factors and you get some statistics. Now, what do you want to take as a proper model for physical situations should depend, I guess, whether your statistics matches to some extent with what you observe physically. And you would, microscopically, I would say, you probably want to deal with this. However, it actually turns out that this seems to work pretty well for some cases. So I'll let you judge it for yourself. So we'll move on and say, yeah.
It's just a word, quantum and particle.
Yeah, so at this moment it's just a word which I am using.
Even quantum particles, if you put them on a lattice 1D, they're distinguishable because their wave functions, you know, I mean, this distinguishability is related to symmetries of the wave function. So even pure quantum particles, if you localize them in space, like you do for a solid,
Oh, yes, that's absolutely
they
true.
become distinguishable.
I guess it's
No?
semantic too.
It
It
is
is
pretty
semantic.
semantic, yes.
So I think it's, for us, it is a little bit confusing, just the words. But I think we can.
So I'll actually give you proper
We have
quantum.
to really case by case, depending on what these things are involved, or
Yeah.
energy level, whatever. I'm sure you're going to tell us.
That is
Or maybe
true.
nothing, just an abstract mathematical. It will be
So
lost.
you'll see, actually, this is a different interpretation, which is more truly quantum in a way, is when you think of this, instead of thinking of monomers and polymers, you can think of energy levels. In this case, you have a certain number of particles which might occupy different energy levels in the quantum system. And then, well, in the simplest case, you order your energy levels, and so then you want to have certain number of particles at a certain energy level. And I mean, you can have Bose-Einstein statistics and Fermi-Dirac statistics. In our case, we pretty much deal with that one because we don't restrict the number of particles occupying the same energy level. And then that is an interpretation, which in fact, some of the original papers which were dealing with Bose-Einstein condensation, they deal with similar type models, and I'll show you pretty soon. So how it comes up. So that's kind of a different interpretation where you forget the polymer type models, but you think of that. So okay, I'm just summarizing and I'm introducing a little bit of a new mathematical object. So let's take 15, which is equal to 1 plus 1 plus 1 plus 1 plus 2 plus 2 plus 3 plus 4. Yeah. So if you think of polymers, that's your picture. So partition of number 15 corresponds to this polymeric sort of a colloidal suspension where you have 4 size 1 polymers, and then couple size 2, size 3, size 4. Yeah. So then if you think of a quantum system like that, so you have particles, 4 particles occupying first level, second level, third, fourth level, etc. And now the object that we will study is actually the mathematical object, which is called Young diagram. Is when you take a corner and then you simply kind of take this 4, put them here. Okay, so then so there is one. No, this actually level 4 is this one. So now level 3, this one. So level 2, there is 2 of them, and then there's 4 level 1. They kind of stuck on top. So I'm gonna make another picture like this in the next slide. But so here I made a comment that in the end, quantum versus classical particles or interpretations, they translate to geometric versus Poisson distribution of the number of polymers of size k, pk. So you'll see it shortly. Okay, so what are we going to study? So once you think of these Young diagrams, so what happens is that when you start increasing the number of monomers in your system, you get Young diagrams which have more and more cells. And if you start scaling out, kind of taking the size of the cell, so here is some drawings for m equals 6, m equals 24, 96 through 84, and I just plotted a bunch of Young diagrams, kind of randomly chosen. So if you scale the size of the cell, in this particular case, it's probably like square root of m, you will see that in the limit, a typical Young diagram, in some sense typical, will actually have a deterministic shape. So even though you start with your completely random diagrams, then as m tends to infinity, in fact, there is what's called a limit shape, a deterministic function, such that any Young diagram with probability 1 will be in vicinity of that function. And then the polymer size density will be related to this function as the negative derivative of this function. So, yeah?
The particles have no valency. I mean, in other words, any number of particles can connect to another particle.
Right here, yes. So you can think of it as an arbitrary number of particles will get stuck into an aggregate. And right now we don't, like for this type of model, it can be done as well. Like there is no internal structure as well. So we don't force any specific internal structure, which I can show you a little bit later if you remind me how that can be done. So yet again, so a little bit new piece, again, the last one. So you have monomers, you make them into polymers, you stack the polymers on top of another, you get your Young diagram. And now the mathematical object which you want to look at is actually the boundary of this Young diagram. So if you think of this function is exactly the size distribution function. So if you think of x here, the value of the function, which is the top of this Young diagram, is the number of polymers of size greater than or equal to k. For example, here, greater than 5, there is no polymers. Now, between 3 and 5, there is exactly one polymer of size 5. Then there is exactly 2 polymers of size greater than 2. Then there is 4 polymers of size greater than 1, and etc. So what we want to analyze how this function f of x and p, which is pretty much a random function, once you prescribe some probability measure on the Young diagrams, so how it behaves. And so in order to normalize this function so that as m tends to infinity, your function doesn't blow up, doesn't disappear or go to 0, well, you need to introduce some normalization. First of all, if you take this function and divide by m, you will get a function whose integral is 1. So the total area of the diagram in this scaling would be 1. And then when you put arbitrary lambda, it doesn't change the integral because, I mean, scaling x, like lambda x, if you integrate dx, that preserves the integral. So now lambda must be chosen appropriately. So and that's something that one has to figure out as you go. That's part of the problem, how to pick lambda so that there is a non-trivial limit to these functions as m tends to infinity. So that is sort of the setup. So what we're going to be analyzing, we'll be looking at measures on Young diagrams pretty much, on probability distributions of Young diagrams, and analyzing, given some probability distribution on the diagrams, can we figure out what happens to this scale distribution function as m tends to infinity. That's the story. Okay, so now it's time to talk about these measures, right? So we work with start with canonical Gibbs measures. So it means that we introduce this Hamiltonian, which is pretty much the energy of the system. And in the simplest case, which is possible to do, unlike anything slightly more non-trivial than that, you're pretty much stuck, is that you simply have energies of aggregates of size k. So whenever you have a polymer of size k, it has energy Ek. And then the total energy of the system is simply sum overall polymers of some of the energies. So it's sum of Ek, Pk, Pk. Let me remind you, it's the number of polymers of size k. So there is no interaction between polymers. So there is interaction, if you want, of monomers within a polymer. That's what creates this Ek, but separate polymers, they don't interact. So, and the canonical ensemble is ensemble on partitions of a given integer. Well, if you're looking at partitions of integers.
Even those interactions have to be almost trivial, because otherwise that Ek would depend on the shape of the aggregate.
Well, that is correct, yeah. So in this case, as I said, there is no internal structure. So, meaning that's exactly why there is one EK. So if you want to have internal structure for the aggregate, like a shape would be an internal structure. For example, you can have.
So there is no size.
Well, there is size K, and that's pretty much the entire.
No,
the only
no, there
thing
is no size of the monomers.
Uh,
Because that will give you.
yeah, okay, yes. If you think physically and like how can some actual physical particles interact to create perhaps some sort of a tree-like structures or physical polymers, then you perhaps want to do that. Yes, but right now, pretty much the only thing which we characterize a polymer by is its size. So there is no difference between a polymer which looks like a tree, which looks like a cross or triangle. As long as its size is K, we just say, okay, its energy is EK, and that's about it. And it could be applicable to some model, so you'll tell me later. You probably know much better.
I'm thinking of a model where that would be applicable.
Yeah. So there is a couple of drawings I'll show you perhaps. And some people, which are much more physicists than I am, have been trying to use them too. So perhaps you convince yourself with some little help of mine that it might work. So yeah, so we take so we introduce a measure which says, okay, so we look at the given number m, the integer number m, and we say, okay, what is the probability that p is equal to big P? So p is a random variable in a way, and big P is some fixed number. So it is simply weighed with the e to minus b beta h of p, beta your inverse temperature. So, and then partition function is simply sum of all p's that partition m. So that's the notation for p partitioning m of these factors. So if beta is equal to 0, that is simply a number, partition number of a given number. For example, if you have 3, 3 is equal to 1 plus 1 plus 1, 2 plus 1, 3 plus 0. So there's 3 partitions of number 3. So Q3 would be 3. Now, as m tends to infinity, the number of partitions increases, and for example, so there is a formula which was found by Hardy and Ramanujan, which kind of gives a asymptotic number of this partition sum when beta is equal to 0. So when there is no Hamiltonian, it's just all partitions are equiprobable. So that's canonical measures. So the canonical measures, they are measures on partitions of fixed number m. So now the next family is the family we actually work with is the grand canonical measures. These are partitions on all measures on all partitions of all integers. So in a way, so there is this extra quantity which I call chemical potential. Again, it's not necessarily entirely physical because usually, so I'm putting beta kind of separate from mu rather than multiplying it. But it's just because in mathematics you don't want to keep writing the product of the things.
Oh, you can do that.
Yeah. So so I'm just saying that okay, let's take this now. P can be partition of just an arbitrary sequence of numbers, such that this sum kpk is finite, meaning it's a system. So you can have any partition of any integer, but it has to be a finite integer, right? So this has to be finite. And then what you do, you pretty much take these canonical measures, and then you add this extra factor, which is minus mu m. M is the total number of monomers for a given system. So you pretty much you take canonical measures for all m's and weigh them with different factors to create the grand canonical measure. And the grand canonical partition function, now I call it as a function of mu rather than q beta m. I have q beta of mu. It's exactly that. So it's pretty much a sum of canonical partition functions weighed with this e to minus mu m way. So it's just a generating function. If you think of q beta of mu as a function of e to minus mu, then it's just a generating function in mathematical language of the grand canonical of the canonical functions. So that is the grand canonical ensemble. So why do you want to consider grand canonical ensembles? And that is quite a trivial observation, but nevertheless it had to be made by someone, and someone who made it was Vershik in '96. In fact, if you look at this grand canonical measures, they actually are product measures. So if you look back at this thing, and of course this is just a sum, EKPK, this is just some KPK. So once you rearrange things a little bit, you can see that for grand canonical measures, probability that number of polymers of size k is given by this big pKs is just a product. And product, it means they're independent. So if a measure is a product of factors like that, it simply means that pKs, numbers of polymers of size k, are independent random variables. And of course, in canonical, that's not true, because again, in canonical, you have a partition of a given integer m. So some kpk for canonical measures is fixed. So therefore, pk cannot be independent. So if you have a number of random variables whose sum is fixed, they cannot be independent. But for grand canonical, it's not fixed anymore, and they in fact are independent. And of course, that's why you can do calculations with it. So now, but of course, if you think a little bit inside of you, you still don't want to, okay, what is this construction of grand canonical measures? I want my canonical measure, right? But the good thing is that it turns out for most practical purposes, these things are equivalent. In fact, there's a general theorem, and that's what was important about this thing, is that these measures are actually equivalent. So if you're thinking of just size distribution functions, then if you can show that there is a limit shape for grand canonical measures, for these measures, in the limit when mu tends to some critical value, then there is also a limit shape for canonical measures. And you can make a correspondence, m will correspond to expectation of mu. So you need to have a thermodynamic limit that expectation of number of monomers tends to infinity, and then in canonical measures will also have the same limit shape as the grand canonical measures. So that's sort of the general theorem which we essentially use. So that is the setup with grand canonical ensembles. And so let me tell you the known results. So what was known before? And pretty much before, people did not really look at Gibbs measures. The reason is that these models, they didn't really use them to describe some kind of a polymeric system. I don't know, I decided to do it, so. And it gives some kind of mathematical things, but people were looking at similar constructions in different contexts. So for partitions, purely partitions of integers, so if you take an integer, take all partitions equiparticle, all equipartition, and ask, okay, what is the distribution of sizes of sums? You know, 10, we represent as 3 plus 3 plus 3 plus 1. So here is, you know, the size, you have 3 polymers of size 3, 1, 1. Then if you ask this question as m tends to infinity, that is the celebrated results. That's the first limit shape, which was pretty much found in this class of models. That's this Virchow's limit shape, and you see that the date actually is 87, whereas here is 96. So this result was first obtained without using the grand canonical versus canonical property. It was in fact done in a rather complex manner using just canonical ensembles, which is much harder. And you have this limit shape. You can take the integral, but usually it's written in this form because that's your density of sizes, right? So that polymer density is here. So you have to scale the, so that scaling factor lambda, which appears in this pretty much the size here, right? The size of the cells. It goes as square root of expected value of m. So I'm just writing for your completeness the partition function. So this is a partition function of the number of partitions of integers, right? So and that's the result for this quantum monomers, partitions of integers. Now, the result for partition of sets, that's Virchow's student. You see, this is 95, so this pretty much you've geared on that, and this already uses this canonical versus grand canonical. This result is obtained in grand canonical setting. So you see, partitions of sets, you have this combinatorial factor, k factorial power pk over bk factorial. So not just that. And in fact, here you have a step function. which I guess is actually not unexpected in terms of, I guess, if you synthesize some polymers, actual polymers, and they create linear structures, you possibly, with given conditions, once you kind of create the thing, so they will be reasonably uniform in size, right? So there will be some kind of Gaussian distribution around the average size, but then most of the polymers will have one size, and that's pretty much what you have. So you, the size distribution function is a step function in that limit, which means that all polymers with probability 1 in the end have same size. And you can, if you scale, you indeed actually get it as Gaussian. And there's certain scaling, so it's some transcendental equation, you can solve it. So that's what happens if you think of quantum versus classical. See, it's kind of interesting, there's no interaction, right? So that's back to the question, so what would hold these things together? So in fact, this is purely entropic. So we're just saying, okay, we have configuration space, which is the ensembles of partitions, and we're just randomly picking stuff.
Well, but you give an energy, so the counting is entropic.
Yeah.
You have an energy.
Not here. Here there's no energy yet. So this is beta equal to 0, there is no energy. So,
well, it's 10% infinity.
It's infinite.
Not zero. Right?
yeah, you can say, oh yeah, beta is equal to 0, yeah. Sure. So, that's purely entropic. So, now you have other ensembles which have been looked at. So there is an ensemble where instead of k factorial, like here, you have k to the power pk. And it's, you can think of this now as internal structure of a ring. So if you take polymer, we have exactly k monomers, and then how many ways is there to arrange them in a ring internally? It's k minus 1 factorial, because you order them and then you connect them, so it kind of removes 1. So essentially you have this extra factor of k minus 1 factorial on top, and so it cancels k factorial. So you have k to the power pk. Now, this model appears in some of the first models of Bose-Einstein condensation, and in fact there is no limit shape for this model. So what happens is that there will be always, as m tends to infinity, there will be, well, I should write probably expected value of m, not m, canonical. There will be always a polymer containing macroscopic number of monomers. So pretty much all of them will stick together, or most of them will stick together. And however, it's not quite a step function, because step function kind of means you can localize what exact size it gets, but it will be fluctuating. So that's
pretty. You have to let mu go to 0, otherwise.
Yes, in this case, mu will go to 0. That is the limit in which you get your thermodynamic limit. Yeah, so you get a thermodynamic limit when number of particles tends to infinity. In this case, mu will tend to 0. That is correct. And so that's pretty much Bose-Einstein condensation, as is known in this kind of, it appears in this model, because it says that microscopic number of particles condense in the same energy level, pretty much. So that's what happens. And there's more mathematical measures which have been looked at. For example, Plancherel measure. I'm not even giving you the formula. It's originally people started thinking of this when they're trying to understand the structure of symmetric group of permutations, because it very strongly depends for particular m what is the factorization of m. So this, what happens to specific symmetric group depends on its structure. But nevertheless, as m tends to infinity, you want to derive some sort of invariant, some kind of things which don't depend on particular m. And turns out this limit shape is one of those things which you can extract from the symmetric group. So there's what's called Plancherel measure, and for this there is also explicitly known limit shape, but it's a little more complex, so I'm not writing it. Okay, so beta not equal to 0. This is where Val and I come, right? And so we start, okay, so let's go back to this grand canonical ensembles, and now we'll look at this EKs. So what happens when you have EKs? And so that's the picture which we had in mind when we started looking at this. So you pretty much want to have this, our chromonic liquid crystals, little stacks, where you have, it's kind of a one-dimensional version of this. So if you think of clumping everything together and having surface energy, which kind of gives you EK, if you have dimension d, it's like EK is proportional to k to the power d minus 1 over d, because the mass is k, so k to the power 1 over d is the radius, and k to the power d minus 1 over d is the surface area. So if you think that your energy is proportional to surface area, so that would be the case. And in case of something like this, you actually will have d equal to 1, one-dimensional, so energy k is a constant. Pretty much, it's the only thing that contributes is pretty much the energy at the ends, because they all kind of stick together, and then the two hydrophobic planes, they contribute the energy. And that's, in fact, one of those models lots of physicists have been considering, so I'm not super ashamed of using it, so people do it. You can also say that there is fluctuation, so it's not quite constant, but perhaps slowly growing. So that's why I think it's kind of interesting to understand what happens also in the case when Ek is not quite constant, but say is logarithm or something. And you'll see this interesting mathematics at least, which appears. So that's when we started working on this with Valerian. So it turns out that pretty much in the context of grand canonical ensembles, there are 5 regimes, and so that's of which 3 are kind of interesting, and the rest maybe not interesting or not new. So, well, first of all, if Ek is much greater than logarithm k, in this case, you cannot use grand canonical ensembles. So what happens? You simply cannot force expected number of particles tend to infinity, because energy turns out to be growing too large. And particles don't want to get into your system. You send mu to minus infinity to wherever you want, and it's not gonna, lure any more particles into the system. So if you want to analyze these kind of energies, which immediately puts a stop on any kind of stuff like this, is that you have to do canonical ensembles. You cannot do grand canonical. Okay, so let's go a little bit back up, and let's try to see, can we do something with something that doesn't grow that much. So there's 3 cases: critical growth, like logarithmic growth, subcritical between constant logarithm, and then constant growth. That's kind of chromonic models. And then there is decay. So for decay right away, I'll tell you, so if Ek decays faster than constant at infinity, you pretty much don't see it anymore. So what you see is the same as if there is no, if beta is equal to 0. So you pretty much see the classical limit shape, which is here now given like that. So limit shape is a Vershik's curve. So we don't see anything interesting. Now for the other cases, there are some interesting results. So if Ek is a constant, that's your chromonic case. So what you get a shifted version of Vershik's curve. So that beta shows up now here. So beta is, for beta 0, that's a Vershik's curve, and for beta non-zero, it kind of shows up here. This is the logarithm, just normalization constant. So you do get something quite interesting. And so the Young diagrams, now there is, remember, for classical case, for beta is equal to 0, there was square root of expected number of monomers, but this one, there will be a ratio of height to length, which is given by e to the beta. So that's, so instead of little squares, you have actually rectangles to get this this function. But of course, you can always scale it back to squares, so we'll just modify some x here. So it's not too bad. Now, in this case, when you're between logarithm and constant, between constant and logarithm, you do get e to the minus x instead of this. So you simply get something that, in fact, also quite often used in various polydisperse physics literature used for polydisperse polymers, this exponential type distribution. So the stretching factor here will depend on mu, and roughly as e to beta of energy 1 over mu, as mu tends to 0. So yeah, the limit will be mu tending to 0 in this case. And then there is a critical case, which is logarithmic growth. And in this case, we have beta less than 1 and beta equal to 1, or beta between 1 and 2 and greater than 2. So, okay, so let's say beta less than 1 for high temperatures, right? So you have incomplete gamma distribution. So you have your limit shape is given by this incomplete gamma function, normalized properly. Now, when beta is equal to 1, it turns out there is no limit shape, but there is a limit process, meaning there is no deterministic function to to which all these shapes of diagrams converge. But in fact, they converge to a random process, which is a Poisson type process, where you start at 0 at infinity, and then as you approach 0, it makes random jumps. So, kind of like, and the density of jumps is given by this e to minus x over x. Beta between 1 and 2, there is no limit shape. Turns out the variance of the boundaries of the diagrams just becomes infinite, and there is no convergence neither to random process nor to deterministic function. And then when beta is greater than 2, then again the expected number of monomers becomes finite. So it's just a little bit too much of a growth at infinity still. So kind of logarithmic growth with beta is equal to 2, that's when your boundary in a way for when grand canonical ensembles are not applicable. So that is the situation. And then a bit later on we worked with Jean Fezu, a postdoc at mathematics department. So we looked at classical ensembles where for those partitions of integers or quantum ensembles, you have pKs. Remember here, they were geometric random variables. Look at this. So it's probability that pk is given by some number is simply some constant to power pk. That's the geometric random variable, right? Now here you have Poisson random variable. So you have where is it? Trace asymptotic change, or yeah. So okay, it's Poisson random variables with parameters alpha k, which is related to the energy. So I didn't write the distribution. And it turns out that the step function, which appears, remember, when beta is equal to 0, that's step function. But however, so you can prove that for any EKs, in fact, which are greater than minus k logarithm k, anything that tends to infinity sort of above that curve, you will still get a step function. So it doesn't really matter. It's pretty much that factor of pk factorial in the denominator of the distribution, partitions of sets, where was it? Partitions of integers. Yeah, this pk factorial is a very strong factor. It just pretty much when the energies grow fast, but pk factorial grows, even faster. So therefore, you do get the step function. For just about any energy, except then once you let your energy like beta ek plus k log k somehow cancel each other, that's when you start seeing some kind of finite structure. And so you get again incomplete gamma function for that class when you have beta ek plus k log k behaving like p minus 1 logarithm k. You get this. So I think here instead of beta I should write p. So that's because beta is already out. So that result was also obtained by different methods by other groups. And then you can have again exponential distribution when you have beta ek plus k log k squeezed between logarithm k and k. So you get another limit shape, which is again e to the minus x. It kind of tells you that you can get similar macroscopic behaviors from kind of quite different microscopic assumptions about your system. In one case you have partitions of integers, in another case partitions of sets, and they give rise to very different distributions of pKs. Now we start running. So how does this work? This actually works in a very simple way. Somehow, because Val and I, we don't like reading other people's work, I guess we had to come up with something, and it turned out to be quite simple. It's pretty much, okay, so limit shape itself will be the expectation of pKs, right? Remember, so the limit shape function is simply the sum of pKs. That's all you do. pKs are your Poisson geometric random variables with given parameters related to EKs, and you take the sums. So limit shape will be expected value. So you look at those things, you take their expected value, you have a sum, and then what do? You simply convert the sum into an integral, which has this very small parameter. So you just keep writing, rescaling things, and so here is an example. If ek is logarithm k, So this becomes logarithm k, so you have k to the beta popping out. You rearrange the terms, and then you see as mu tends to 0, this is pretty much converging to an integral. You need the little mathematical theorem says that it does converge, but otherwise that's the converted. So limit shape has to be given by this. Now, the only thing you need to do is you need to control the variance. You need to make sure that it's not just the average which converges, the variance tends to 0. So you do pretty much the same. So there is a Kolmogorov inequality which allows you to control the variance, and that's where you need the multiplicative property. Multiplicative property says that if you have sum of independent random variables, then the variance of the sum is sum of the variances, and it can be done pretty easily. And that's, again, I give for that example, which is logarithm k, you get some, for the variance you get some rescaling, and then there is some factor, magic factor, mu to power 1 minus beta. So when beta is less than 1, you get variance disappearing, and you get pretty much your limit shape statement. There's not much else to do. And so that is entire calculation. For all the other things, it kind of works the same, even though for slightly more general versions, you need just a little more general versions of these calculations. I have about 1 minute or 2 minutes, right? It's kind of like that. So, but probably won't be needed. So I'll just briefly give you exposure of what else we have done. This is joint work with Sundar Siddharaman and Jenfei Zhu, where I was mostly in a consultant capacity, and Jenfei was doing, of course, all the heavy mathematical work with estimates and inequalities. Okay, you want to maybe do some dynamics. In fact, the dynamics is not very physical, and that's our main thing, is to actually make it more physical. So you can think of this, you can add and remove monomers to polymers, right, with some, so attach or detach. So in language of Young diagrams, that would correspond to adding and removing corners, and these kind of models appear also in other contexts too, like crystal growth or whatnot. So there's certain rates for adding and removing corners. So now this is a new mathematical picture which was used by Jenfei, is to actually look back at the particle description. So there is 4 particles at level 1, then there is 3 particles, say 2 particles here at level, no, here is actually 3 at level 2, then 1 at level 3, and then 1 at level 4. So it's pretty much like gradient, 1, 1, 1, 2, and 4, right? 1, 1, 2, and 4. So you can think in terms of particles, you get what's called zero range process. You have particle which kind of jumps right and left. So when you add a corner or remove a corner, your particle jumps to one side or to the other side. So and that is the model. So model of our dynamics was you have this bunch of particles on a lattice, and you pretty much hop to the left with rate 1 and hop to the right with rate which is proportional to that energy difference of each case. The rates, okay, if you think about it, they're not necessarily super physical, but that's what we did as a first try. So what was known, for example, so if you do a diffusive scale, there was a reasonably recent paper of Funaki Sasada, then you actually, so you rescale space and time and look at empirical densities of particles, they will converge weakly to solutions of this PDE. So it's a nonlinear PDE. And the Virchow curve is the invariant solution, or stationary solution of this PDE. But, so the methods that they use are quite different from ours, and also they relied on the fact that this Virchow curve is actually infinite at 0. So there is sort of an infinite reservoir of particles at 0, which constantly exchanges with everything. Whereas in our model, we actually did a finite, so we didn't have infinite. Remember, the limit shapes that we had, they actually didn't go to infinity at 0, they were finite. So it's quite different. So this is just a quick review results without any additional comments, so that you get the same, obviously, when Ek is about 1, well, delta Ek is 0, so it's as if there is no energy. So you get the same PDE, however, there is only one invariant solution which goes to infinity, it's Virchow's curve. And remember, the stationary solutions for now will be the limit shapes that I showed you, and they don't go to infinity. So whatever you start with in the beginning for an integral, so that's what it says. So you have directly a boundary actually for these PDEs, which are preserved. So that's what happens for Ek about 1. Now when you have between logarithm and 1, you have a different PDE, and then when it's like logarithm, there's a different PDE with a different factor. And notice these are linear PDEs, unlike nonlinear, because what happens is that so this rho over 1 plus rho, once your Young diagrams don't scale as like little blocks, but scaling changes with mu, in fact, you pretty much linear, these things become this linearization. So one of them just scales out. And so you lose non-linearity. So that's the dynamical story. And so we're also looking at version 4, in fact, partitions of sets for the classical, so to speak, polymers that hasn't been done yet. And so now with Genfei, we also have done some additional stuff. This is in language of large, I'll actually skip that part and I'll just come here. So in language of theory of probability, there is large deviation theory for which what's called action functional corresponds to free energy for in physics language. So it's pretty much the free energy of a system whose rotation density is given by rho. And so you can derive, in particular for a case of chromonics, when in case of out constant, you get a free energy which looks like that. The important now questions to finish is, okay, how can you add the orientations finally? So, and combine this with Ansager's model. So it just partly goes with what happens when polymers are interacting, because Ansager's model is pretty much a second-degree approximation for interacting particles. But this is all for the future. But at least we kind of understood how one can mathematically do the size distributions to some extent correctly, not necessarily physically justified, but like from a mathematical standpoint. And I think I'll just end here. Thank you for your attention. We made it.
If you change the interactions, the size distributions will change as well.
If I change what?
The interactions. Or even if you just put orientations. I mean, your size distributions depend on the interactions between the particles of the monomers. Forget if they're quantum or classical.
So that is correct. So in this case, these EKs are pretty what controls the size distribution, the limit shapes. And if you change your EKs, like you get different results. So yeah, if you're depending on how these energies behave for large sizes, you get different limit shapes. So if you think so physically, deriving the asymptotics of EKs is the question which you would ask a physicist. So which effects do you need to consider and how do you get them? So this is what you could possibly ask.
You cannot solve it, yeah.
That is true. Well, as you know, as a mathematician, the best I can do is I can say, okay, if you give me a case, so this is what happens. But deriving those EKs from physics situation, that's a kind of a different story, which I'm not really telling.
Yeah, didn't you already assume that they interact face to face or face to end, and then if that is the case, you have a kind of pseudo valency of 2 because they do not attach naturally, isn't it?
Yes, that is correct. So in this case, it's pretty much a valency of 2 if you want. So, but of course, physics is complicated, and so we call this like internal energies, but in fact, all of these are in some way some free energies. So because free energy is kind of a renormalized energy, right? Once you coarse grain the system, what used to be we consider like internal microscopic energy, it becomes free energy on a larger scale, and et cetera, et cetera. So you now know for sure what's happening. At least I don't know for sure what's happening, but at least for the models with this kind of picture where you have the stacks and the energy pretty much comes from the boundary. Oh, I'm pressing wrong buttons. This is what you get within framework of this model. Now, if you look at the size distribution and say, okay, is this a reasonable approximation or not, that will tell you, am I bullshitting you entirely or not? Because I can simply say, if you look at partitions of integers and put Gibbs weights, which are constant, pretty much as dependent number of polymers, each polymer gives the same contribution. So this is what's going to be the limit shape. And if you take funny enough, partitions of sets as the base model, then in fact you'll still get a step function. So you'll get a step function with a little bit of Gaussian scattering around the mean value. So whatever is better for your polymeric system, that's probably what you see. Now, once I was looking at the literature, there's lots of stuff, and it's hard because actually even determining distributions of these things is quite non-trivial. There are very indirect ways of doing it. For true polymers, you can try to use a centrifuge or something, but for aggregates like this, like say chromonics, I haven't found lots of convincing data about like exact details of distribution of sizes, and they have internal structure, which makes it harder. So, like those which, let me go back to what I stole, like when I talk to Oleg, he suspects quite a lot that these kind of shapes, they contribute non-trivially into properties of what they measure. So when it's this, see, it's not just stacks, but some kind of Y structure or something.
But that's one possibility. You could have a house of cards type interaction because these are normally aromatic. Yeah. And if they have a charge on the rim, then the preferred orientation may be this.
Yeah.
This happens, for example, if instead of having chromonics, you have platelets of clay, things like that. Yeah. Laponite, things like that, which people actually do observe also. Yeah. This type of structure. So that also is not obvious. But in the dynamic model instead, it's not obvious to me if okay, so you have a stationary state which would correspond to the zero eigenvalues. The equilibrium one. Mm-hmm. So that is kind of not surprising.
Yeah.
But don't you have the possibility of an interaction so that when they eventually get together, they never depart again, or instead that they can break apart? One is the kind of flocculation type model, isn't it?
That is correct, and that's why I'm saying that this is not particularly. So you see. So that you see, that's why what I'm saying. So in this case, actually, for example, I don't break. So if you think about what's happening, this adding and removing polymers like this, I pretty much always I take my polymer and I either add a monomer or remove a monomer. I don't actually break polymers, and I think especially if you think of using some kind of a mechanism for like even elasticity when you think of elastic constants, so the suspicion is that these linear structures, they break, allowing polymer to bend, and this kind of dynamics that doesn't have it. So that's why I will not particularly insist that this is truly physical. It will take all the facts into consideration. In terms of mathematics, that makes it a very non-local problem. Like here, you have a particle which hops right and left, because you pretty much create, you add a polymer, you add a monomer, or remove a monomer, so it just creates a easy hopping. Once you start breaking polymers, you pretty much have non-local jumps because you have a polymer there and it breaks, it hops into something. So it's much, much harder mathematically to analyze. We cannot do that yet.
But if you only have near-neighbor interaction, you can break in the middle because all you miss if you break is that particular bond. It would be different if you had more kind of collective interaction.
If you break in the middle, you have two ends. If you just break in the three double ends.
Well, in terms of modeling, yes, but if you think in terms of a locality of interaction for the polymers, you have in this model, if you look at the generator of your process, it kind of connects pK with pK plus 1 and pK minus 1. Because you have pK, number of polymers of size k, and when you change, add or remove a monomer, you simply subtract something from pK and add something to pK plus 1, right, if you add a polymer. But now if you break it, you take P100 and break it into two parts of P50, so you jump from 50 into, from 100 to 50, so it's highly non-local mathematically in that sense, and lots of machinery which you need to, to prove anything, it just requires some locality.
So if you consider it as a stochastic Markov process, your transition matrix, instead of being nearly diagonal band, it would be
just right. Yeah. So much of this is like when you do the proving, you have some kind of stuff which happens on the average, which gives you the equations, and then you need to show that everything else disappears, which kind of spectral gap of some sort type estimate. And then you have matrix which is already almost diagonal. You can understand that it's probably not that hard to do it. But once you give me a full matrix, you pretty much, cannot do it. So that's like in plain words, that's the problem mathematically.
Any more questions? Okay, so let's thank Ibrahim again.